Hi, hi everyone. My name is Dilip Kumar Munagapati, and my student ID is M00908451. Well, this is my coursework 2 of PDE 4431, which is robot manipulation. In coursework 2, we have to design, we have to make a robot simulation in MATLAB using GUI. Well, in that GUI we have to define few steps, which is I'll just show you in a minute. So as you see, the left hand side is the theta values which we are giving for forward kinematics to get the end effector of the robotic arm. Here I've designed a 6 DOF, which is 6 direction of 6 DOF axis of robotic arm, and which has 4 links. And let us suppose I'll just I'll give you an example of doing this to start from the home position and just giving the 000 as the reference. As you can see, it is in the 0 or home position, which has 3 links. Actually it is 4, but have make did it in a such a way that the center part and the last wrist part must be spherical kind of thing, so that the base can be rotate in rotate in z axis as well as in uh, y-axis. As you can see, this is the y-axis and this is the z-axis. This can be rotated in along the z-axis as well as the y-axis. And as you can see, this is the position of the end effector, this thing. And as you can see, we have inverse kinematics as well, like giving the positions and letting the robot itself make the decision, like how much theta values can be implemented and do the stuff like 100 minus 200. And so a position of x is this and this, and make it an inverse kinematics. Hopefully this should work. Oops. So as you can see, like giving theta value 6 theta values to the joints, and it converts that like it gives the px, py and pz of the end effector of the robotic arm. Well, this is the this random numbers, random, it's not random, but there are having a restriction of angles for each joint. So this is the like very like bare minimum range of these joints I have given. So this is in that position, and let's make it to like 50, 100, 100. So which it determines the in x position of the end effector. In x-axis should be 50, similarly y-axis should be 100, and z-axis should be 100. So when I put it in click on the inverse button, this should go to that particular position. As you can see, it just moved to that position. As you can see, this is a y axis, and it is accurate. It is very accurate. In y-axis it is at 100, and z-axis it is at 100, and in x-axis, as you can see, this is in 50. Okay, so that's how the inverse and forward kinematics works. To summarize this inverse and forward kinematics, like in forward kinematics we are just giving the joints angle of at which position that particular joint should be there. by giving that joint, and we'll be getting the output of the positions of the end effector. That's how we are calculating the forward kinematics, by giving dh parameters, like each joint, giving each joint a link to the dh parameters and doing stuff. I'll just show you in a minute. And coming to the inverse kinematics, we are giving the position where the robot, the end effector should be there, and it should decide its own theta values of each six joints, so that there is no restriction of each joint. So that's how the inverse and forward kinematics works. Also you can see there is a pick and place like push button which I have added. So what it does is like picking up. So it starts from the home position. I'll just show you in a minute. It starts from the home position and go to approach position and pick and go to approach again, and move to the approach of that particular placing position. I'll just show you. Okay, as you can see, it started from the home position. Okay, it started from the home position and it's picking up, going for the pickup. As you can see, the advantage of having 6 DOF is like we can rotate the wrist at the end of this effector, and we have having very advantage of having this in the base also, and it is picked and moving to that particular location to place it, and it loops it again. Start from the home and go to approach and go for pickup and go and place at the particular self. So that's how this has been designed. The coordinates has been given by me, like from where it need to be placed and from where it should be started and etc. So that's how this GUI like from my end has been worked. I'll just explain you in a minute how the function whenever I call the push button. Okay, I'm just closing it. Okay, sorry for the interruption. Okay, whenever I call the push button function, as you can see, this is the push button of the forward kinematics. It picks up these particular theta values of 6 theta values and convert that into a string, like string to double. It already in the string format and convert that into a like double type data type, and so it converts that into a degree format, which is which is the main part we have to see. And these are the links, 6 links which we are using, but I'm using only 2, 3 and 4 links to visibly I'm just using it, and the link 1, 5 and 6 are in between the joints. So this is the like parameters I have using this thing. So first one will be A, and second parameter is this thing. Okay, sorry. So this is how we are going to define the robot model, and the name of the robot model is like 6-axis RRRR robot, and here is the main part which is converting that values into the like th parameters values, transforming from 0 polling to 1. So it is calling the function which I have made previously. This is the dh function. As you can see here, there's a tab open. So it is calling this function. The first parameter is length of the arm, second is the alpha, like the rotation around the z-axis, d is the joint to joint length, and theta is the value which the arm is rotated towards. So that's how it assigns the value and calculates the theta values, positions, and etc. So after like getting the transformation matrix for each joints, and that's how we are after multiplying we'll be getting a final transformation from 0 to 4 links. I'm just assigning the like the variable to it actually, and in that there should be the final this thing, uh, I'm just calling the fourth column of row 1 2 3 values to x y z, which is the position of end effector, and like plotting that theta values in as you have seen that, and converting that into a string format, number to string, and floating it down, which is floor. Here I'm used floor because the values may be in very much decimals points. I'm just flooring it down just for getting integer values. So that's how the forward kinematics has been done. And coming to the inverse kinematics, so I have used a predefined function over there. We'll be defining px, py, pz from the GUI and getting that into in number format, data type, double data type, and the same the link robotic arm have been used, name is also same. So here the transformation matrix I have used is this thing, px, py, pz, and here the inverse kinematics predefined function is have multiplied with this t, and this is the mask matrix, and this is also, so this is the phi, theta, and alpha values which we are going to define. This is the main part. Now robot is going to be turned, and this is a mask matrix. If the robot has 6 DOF, it has to be in this particular format as per my research. So I'm converting that into radians to converting that into degrees and making that into a string format and pasting outside this inside in the GUI as theta 1, theta 2, theta 3, and theta 4, theta 5, and theta 6. So that's how I'm placing it, and finally I'm just plotting it. Into the GUI. So that's how the forward and inverse kinematics has been done. So here the pick, whenever I push the pick and place, I have assigned a tag name called simulation over there, and I'm using a predefined model just to make sure it works perfectly. And I have assigned h1 home position, h1 is approach, and this thing, and a1 is approach, and hover 1 and hover 2, which is hover 1 in the sense like picking up the point, a1 is the approach point, c is the contact point, and the same thing, h2 is the place point. So that's how I'm converting that into trans file, so that to convert that into matrix, and see trajectory from home position to theta 1, I mean the first point. So that's how the trajectory has been decided, converting that into a transformation matrix using the concatenation in 3D matrices. So that's the reason I have used this here 3, and using inverse kinematics which has a 6 DOF. The RU is something like right arm and elbow up, as you can see in the rotation of the articulated robots. So these are the spheres, and for just representation of the points in the GUI, and plotting that in the GUI and looping it up to make continuously pick and place the things. So that's how the GUI and MATLAB project went. I'll just show you the guide as well, GUI. So how I've designed it. matlab projects, yeah, this is the one, RRR robotics. So this is the main part where I have designed the things. So as okay, when I double click on this forward button, push button, so this is the tag which I have named, assigned it, and this is a string which is displayed on the GUI, etc. The similarly I have assigned the same thing for everyone, every push button, and the axis has been drawn from this particular point. So that's how I have designed this GUI, very simple and simplistic way. Just assigning like type these theta values and click on the forward for forward kinematics, and just enter the px, py, pz for the inverse kinematics, and for simulation, continuous simulation, click on this button. That's it. Thank you. Thanks everyone.